Good afternoon. All righty. Hi. So we talked since quite a while about acids and bases, and we talked about a strong acid, and we know that a strong acid dissociates completely into its component, into H3O plus and into the respective anion. A weak acid doesn't do that. Some of it goes to the right side to the products, but lots of it stays with the as reactant. And so we have to treat them differently. It's easy to calculate the pH of a strong acid, but it's very difficult to calculate the pH of a weak acid. But I've shown this to you how to do that. And so we talked then about titration of a weak acid with a strong base. And this is the titration curve. This is the pH here. And this is the amount of base, strong base that you have added in order to titrate the weak acid. So at the beginning, nothing happened. You have the pH straight here. You can calculate that. We have done that. And then you have that buffer region here where there are hardly any changes in pH happen as you add OH minus, as you add base, because it's a buffer. And we have talked about the equivalence point, that the equivalence point, initially you have a pH of 7, but this is not the end of it, the equivalence point, because the acetate ion reacts with water to form again undissociated acetic acid and some OH minus. That means the equivalence point is a little higher than pH 7 because you have that OH minus in there. And then you get anything you see a curve like this here, you get for free, you get the half equivalence point. So this is the equivalence point. The distance half the volume from here to here, you have this. That's the half equivalence point. The concentration there is the undissociated weak acid and its conjugate base is in equal concentration at the equivalence point. And with this, if you go across here from your half equivalence point, you go across here, you read the pH, and the pH is then your pKa of that acid. So you get this for free. If I show you a weak acid titration or weak base, and I ask you, what is the pKa of that base? You just go into the buffer region, you go to the half equivalence point, you go over and read the pH, and with this, that's the pKa, all right? Good. Yeah, that's essentially what we talked about. So let's see how well you know all this stuff. We have in yellow here a nitric acid, HNO3, okay? That's a strong, strong acid. That means K is much larger than 1. And we titrate this with a strong base, with KOH, and we get this curve here, that yellow curve here. This curve or this curve or this curve, they're all the same. If this is the pH and this is the amount of base that you have added. So you go along in your titration here from left to right. So now I'm going to take the nitric acid in my jar, in my titration vessel, and I dilute it by a factor of 10, okay? And now I do that same titration again. That same titration with the same strength of a strong base, sodium hydroxide, or KOH, potassium hydroxide. And I want to know from you, which green curve is that new titration curve? Is it this one, A, or B, or C? And by doing so and answering this right, you show me that you understand this whole business with the strong acids and with dilution and so on. And let's see if you do. Give me your answer, please. 30 more seconds. Okay. What was that? They should click in, huh? But they see it up there, don't they? Or are they blind? Ah, yeah. Okay, got it. He is right there. He's right there. Click. Okay, you did it, huh? Now he's leaving. Oh, you embarrassed him. Oh, okay. All right. Let's see if this still is so much fun if we see that result here. You know, there's something, you paid a lot for that book, you know. Why don't you, some of you, read it, okay? And that's sort of, it's better than doing it like 2 hours before the final, okay? Now, let me explain you a couple of things. Explain to you. So, if you have a nitric acid, and you have this in a certain volume, and now you give the concentrations in mole per liter. Now you're going to dilute it by a factor of 10. Do you have the same amount of HNO3 in there still, or do you have a different amount of HNO3 in there? The same amount, okay. So if you titrate molecule by molecule H3O plus with OH minus, okay, to make water, all right? So that would give you your equivalence point. So of course, in moles per liter, the concentration went down by a factor of 10, but not in effective amount of HNO3. That's the first thing. Now, if you have a strong acid and you dilute it by a factor of 10, pH is the concentration, and the concentration of the H3O plus. So thus the concentration, that's in mole per liter, change. Of course it changes, okay? So what does this do to your pH, to your initial pH? So it has to go up or down or something like this. So you can see this here, that's funny looking here, or this here, okay? So, and then you have a diluted solution of nitric acid. And with this, you put in your your potassium hydroxide. Of course, it also gets diluted. You know, if it's 0.1 molar sodium hydroxide and you have a 0.01 molar nitric acid solution, you have all this volume. So, of course, the change of your final OH concentration will be also different than the one which you had not diluted. Okay? So why don't you think about this, discuss it with each other, and give me an answer that is acceptable to me. You really got to know that. Yeah. So what is it? That would be C. Would that be a higher pH? Would that be a higher pH? How can the pH be higher there if you had 0.1 molar to begin with? A strong base?
Yeah, it goes to a weak acid, right?
Yeah, sure, because it doesn't want to give away the right? Yeah. But what does that mean? Forget about it. Just think about it in a different way. Don't forget strong base. That's a strong acid with a strong base, okay? All right, let's have a look at this. Don't give me a heart attack, please. Okay. I go with A. I hope it's right. I don't have my notes here, so. No, it is right. It's got to be right. All right. So obviously it is right, okay? So here, your pH, that was, let's say if we had 0.1 molar HCl, what is the pH? 0.1 molar HCl, what's the pH? 1. Now, I dilute by a factor of 10. What's the concentration in moles per liter? 0.01, 10 to minus 2. What's the pH? 2, okay? That's right there. Now, I diluted it, and now I keep diluting my sodium hydroxide, okay? I keep adding that sodium hydroxide when I'm past the equivalence point. Of course, I'm diluting it now by 1 pH unit, because I had it before, it was 0.1, but it sees all this water, so the concentration in moles per liter is diluted. With this, the pH at the end goes down by 1 unit, and the equivalence point, it has to be the same, because I'm just doing molecule HVO against molecule of OH minus. I didn't change the molecules of HVO plus, I changed the concentration, molecules per liter, but the amount is the same still. Okay, so with this you have here, that is the same equivalence point. So 10 times dilution is 1 pH unit up, goes from, and then the moles of HNO, that's not the molarity, it's the moles of HNO2 is unchanged. So the equivalence point stays unchanged, and here I dilute by a factor of 10. Any time the base hits that solution, it gets diluted by a factor of 10, okay? So it was 0.1 molar, but essentially it becomes 0.01 molar once it hits that solution. And with this, you go down by 1 pH unit. Okay, so we did this one right. Now let's go and kick it up one notch. We have now a weak acid, and we titrate it with a strong base. So this is my initial curve here, the yellow curve. So now I dilute it by a factor of 10. What happens, and now I titrate with this same concentration of KOH, how would that curve look like? Would it look like A, like B, or like C? Okay? So think about it and give me your answer, please. Does the pH go up by 1 unit? For a weak acid? Just adding water. HAC plus H2O gives HVO plus AC minus. So we add water. What do you do? What's the answer? You're thinking it's wrong. What is it? A? Think again. Yeah, we're getting there. We're getting there. Good. But we are not quite there yet. Why don't you discuss this with each other? Okay. So obviously the pH, will it go up or down? It will go up. Will it go up by 1 unit? No, okay. So that's probably 1 unit here. That looks funny here. That could be, that's not the whole unit, and that's not a whole unit, okay? Now, what happens to the acid at the end when you are just putting in OH minus, and the acid is all gone? Are you diluting that OH minus? Yes, of course. It was 0.1 molar, and then you just dilute it because you have all this volume there. And so you go from 0.1 molar to 0.01 molar sodium hydroxide. So this must be then the one. Now, this must be the answer already, okay? Why don't you discuss this with each other, please? And what I said about the equivalence point for strong acids is probably also true for weak acids. Not very lively discussion. Have you given up or what? No. Good. Don't give up. There's still 240 points to be had. Some said, just go with the majority. And some said, you know what he said made some sense to me, okay? And some said, yeah, okay, C is down here, okay? All right, let's see if it's C. I would go with C. I hope it's right. Oh, yeah, good. All right, good. So what I said here, of course, you're putting water in, it shifts the equilibrium to the right side, it makes more H3O+, but it's not making a whole pH unit at 10 times more, okay? It makes a little bit more. That's how these curves look like, and it goes straight here then, okay? So that's smaller than 1 pH unit. Now, the interesting thing is, what I didn't tell you, is the buffer region. Now, the last time we talked about if you dilute a buffer, a good buffer, by a factor of 10, it doesn't matter. It's still a good buffer. So the buffer region stays unchanged. And just for fun, this would be the half equivalence point. This would be the pKa here, okay, if this is the pH. All right? So it stays unchanged, the buffer region. And of course, the equivalence point stays unchanged because the amount of H3O plus is the same about, okay, that you deliberate when you dilute it by 10. And and this here, you just keep diluting that stronger KOH. There's nothing happening anymore. You just keep adding. You could go to here. You keep adding KOH, but you have all this dilution in there now compared to the one before. You dilute it by a factor of 10, and this is 1 pH unit here. The equivalent point stays unchanged, and the buffer region stays unchanged. And with this, we didn't discuss this here in my. So this was the answer. All right. So today, we're going to talk about something which I have talked already about a little bit. And these are multi-protic acids. These are acids that have more than one proton, more than one H plus ion that can go off that acid, can dissociate off. So it would be, for example, you have H2CO3, there would be 2 protons going off. First one, and one equilibrium, and then the second one. And we talk about this. So this is multi-protic acids. They have more than one acidic proton. If we talk slang, we say this is an acidic proton. It means this proton goes off, that H plus goes off, and then we say this is more acidic than the other one. So that means it go off, the more acidic one goes off at a much lower pH than the less acidic one. Slang, okay? And you will need this because many of you go into medicine, hopefully, and to microbiology and chemical biology and all these different fields and biochemistry. And so you will need to understand about buffers and about polyprotic acids, and this is what we're going to talk about there. You met one of those, actually you met more than one. A polyprotic acid, for example, is thymol blue. It has the thymol structure, and then this has two protons on there. And the nice thing is that they dissociate successively. First one comes off, and then the second one comes off, so you have two pKa's. And this is that molecule here, H2 thymol. So this is sloppily written, okay? So you could write here H2O, and here you write H3O plus, okay? But very often when you don't want to write always the water in there and you don't want to write the H3O plus, so this is the same than if you write here H2O and here H3O plus. So this is that equilibrium here, and this is blue, and this absorbs to appear yellow, okay? And the pKa is 2 of this, so if you are at 10, so the pKa is 2, the pH 2, what's the concentration of this and of this at pH 2? What's the concentration? pKa, pH is pKa, so this would be this concentration and this concentration at pH 2 would be the same, okay? Now, if I say pH 1, would I be more on the right side of the equilibrium or on the left side on the equilibrium? On the left side, okay? pH 1, this is not really deprotonated. If I have this equilibrium with this pKa at pH 1, I have really all the protons are still on that molecule, okay? And if I go to pH 3, what do you think? Do I have this form more or this form more? This form, of course. pH 3, it's above the pKa. pH 3 says that I have mostly the right side, and pH 4, everything is on the right side. Yeah? So now the second equilibrium here is this ion has still a proton, and that proton, if I react it with water plus H2O, gives the thymol 2 minus anion plus H3O plus, or H, we left the water out, it's H3O plus. And this has a pKa of 8.8, so this is 10 to the minus 8.88 is the Ka, so that's a lousy acid essentially. So what pH would I be able to have this and this concentration the same? What would be the pH? What pH is this and that concentration the same? It's a weak acid, obviously. Nobody? Are you serious? Well, let me go back. Okay. All right, we talked about buffers, didn't we? Okay, what is this point here? That's the equivalence point. If I go halfway, what's this here? Half equivalence point. What's the pKa is equals the pH here, isn't that right? Okay, so let's go forward again. What pH would I have to have that I have this and this in equal concentrations? pH 8.8, exactly. That's the half equivalence point, all right? So if I'm at pH 6, what do I have more? This here or this here? Left side or right side? Left side. Left side, okay? So if I want to bring this all in this form here, would I raise the pH far above 8.8? Yes, I go to pH 10, and then I shift it all to the right side. Right? This is very important that you understand this, because it's important. Amino acids will do that, and protein folding is very important for that, to understand how this works here. So now that means I have just two. If I would have a titration curve for this here, this would be a weak acid. And then I would get a second one for this one here. So this would be the first one. This is my equivalence point for this here. That's the equivalence point. What's this point here? The pKa. What's the value of the pH? 2, okay, because this is my pKa. Now, this is the second. This is the second buffer region, first buffer region, second equivalence point, okay. What's this point here? This point here, between here and here. What's this point? That's the buffer region, right? The buffer region of this baby here, okay? And what is the pKa? 8.8. What's the pH? There you go, okay? You go down here. Let's see if I have, there it is, okay. That's pKa 1. Now you understand it, half equivalence point. That's the equivalence point here. You take half the volume, you go here, go up, go across, read it off. Now this one is the second half equivalence point. You go from here to here, okay? So from this equivalence point to this equivalence point, that's the full area, and you half it, and you go across, you get your pH, okay? So if I'm above the pKa, I'm having the protons off, they are dissociated, okay? But I have to be significantly above, otherwise there are still some undissociated ones. If I'm below the pKa, then I have it in the, still in the form where the proton is on, okay? So, and the nice thing is that this has color. They absorb differently, these ions. And so this, for example, at pH 2 is sort of yellow-orange, and further down it's sort of pink-red, and then it goes into the yellow here. At pH 7 it would be yellow, and then it goes up and gets light blue, and then it gets darker blue if it goes into the basic side, all right? So you did titrations where you put an indicator in your solution, did you? Okay. And the indicator is something like this, okay? But you were told only to put 1 or 2 or 3 drops in there, not a whole load of this, because it would totally mess up your titration, because in addition, you're titrating your indicator, okay? So you want only a very small amount of the indicator that it doesn't affect the titration of your weak acid or your weak base, okay? All right, this is an important issue. So let's have a look at, let's have a look at how this looks like here. I have this indicator here. If I could have the lights on, please, and the camera for this. This here, please. Okay, so this is pH 7, water, and this is water where we're going to put an HCl, and there we put sodium hydroxide in there. So I put a little bit of HCl in there. Who says that's not HCl? Yeah. Backseat driver here. He's trying to help me, which is very nice of him. So is that base or acid? What an ugly color, huh? Okay. So that's acid. That's the red area. That's the acid area. And now we're going to use some base. It says sodium hydroxide here. He thinks I'm senile, probably. Okay. So we put a little bit of base in there, and it's blue. And anything in between has shades of these colors, okay? So this is how a diprotic acid acts, and this specific acid acts as an indicator. All right, good. So you've seen that now. Don't use so much indicator, because you will otherwise titrate the indicator and not your unknown weak acid or weak base. Okay, good. It's Friday. So polyprotic acid, I already alluded to this. We met that acid the last time. That's carbonic acid, H2CO3. It has 2 protons that can dissociate. H3 PO4 is phosphoric acid. There are 3 of them. First, the first one goes off, then the second one, and the third one. So you have 3 pKa's, you have 2 pKa's. Sulfuric acid, H2SO4, has 2 pKa's, the pKa1 and the pKa2. And so the pKa1 is smaller than the pKa2, is smaller than the pKa3. Let's do it the reverse, okay? Ka1 is larger than Ka2, and Ka2 is larger than Ka3. So it goes relatively easily. The first one goes, you can remove the first one. That's the larger Ka1, okay? And then the second one is not so easy to remove because you have your negative ion now, and you try to remove a positive ion from it, so it tries to hang on. And the third one, you have a twice negative, and it's much easier, much more difficult to remove. So let's look at this here, and I was lazy again, but now I was only half lazy. So I didn't write H2O here. So H2O plus let's see, carbonic acid, H2CO3 plus H2O gives H3O3 minus, but hydronium ion, H3O plus, okay? So that's the first one, and that pKa is 6.37, or 10 to the minus 6.37 is the Ka, all right? So if I am at pH of 4, which form will predominate? This one, number 1, or number 2? This one. 1. Now I'm at pH of 7.5. Which one would predominate? 2, exactly, good. So now we have this here, this HCO3 minus. It reacts with water to form CO3 2 minus, the carbonate anion, plus H3O plus. So that's the second one comes off. And that means the pKa is 10.25, or the Ka is 10 to the minus 10.25, okay? So I'm at pH of 7. Would I have this here, or would I have that here? This one, left, okay? And I go now to pH 12. Which would I have? Would I have any of this left here? Would you have just this here? At pH 12, you have just this left, okay? So this is our titration curve. Now we know again, half equivalence point, that's for this, the titration for this. Half equivalence point is, the pH scale is the pKa1, 6.37. The second half equivalence point, pKa2, and that's it. And here the equivalence point, here's the other equivalence point, and the rest we don't care really about. All right, so let me ask you a question. And I would like to have this one here up on this screen, the left screen up on the main screen, please. And the question is, which carbonate species is present in the highest concentration at pH 7? Here are your data, okay? Oh, you can read it. Oh, that's wonderful, just wonderful. Okay, what was that number? That number was 10.25, and the other one was 6.37, all right? So which carbonate species is present at the highest concentration at pH 7? This one, A or 1, or this one, B or C? Why don't you give me your answer, please? That should be easy. You nearly gave me a heart attack here with your pKa. Does this read really sodium hydroxide? KOH. Ah, okay. Sorry. You can't. Okay, so at pH 7, we are above the pKa, okay? So we should have this here, huh? Is that what you say? Yeah, that's what you say, at least 157 of you. And I agree with that, actually. Let's see if I'm right. All right, so we have here, this was the one where we have HCO3 minus plus water gives, no, that's the one. H2CO3 plus water gives HCO, so now I wrote it correctly. You see that? Gives HCO3 minus plus H3O, pKa 6.37. We have pH 7, okay? So we are on this side more, okay? Now, this one here, HCO3 minus gives to CO3 2 minus plus H3O plus. That would be, I would have to go at least above 10 here to get this here, substantially above 10. And with this, I agree with you that this should be the species which has the majority. Okay, you understand that. That is excellent. Good. So let's talk a little bit about our blood and the buffer. Our blood is buffered. So many of the reactions that happen in our body require buffered systems, and they are very, very sensitive to pH. And if you look, for example, at blood, the blood has a, so the regulation, for example, when you breathe in, the CO2 that you breathe in, the pressure is about 40 torrs, okay? Now, that gives you a concentration of 1.2 millimoles of CO2. That's through the lungs, okay? And then you have another regulator, so that's just Henry's law. You have another regulator where you have carbonic acid, and this is a carbonic acid anhydrase, that's an enzyme. It regulates the rest of the CO2 regulation is through your kidneys, okay? In your kidneys, you're maintaining a concentration of HCO3 minus of 24 millimoles. Okay, now we can calculate the pH, so that's in the kidneys. We can calculate the pH, is the pKa, okay, the pKa plus the log of HCO3 minus divided by H2CO3. So that would be 24 divided by 1.2, that's 20, okay? And the pKa at 25 degrees is, it was 6.37, but your body doesn't have 6.37, 25 degrees, so the constant is different. You know that the equilibrium constant depends on the temperature. And with this we have, it's 6.1 at 37 degrees Celsius, the pKa of this equilibrium here, not 6.37, it's 6.1. So we take the logarithm of 24 divided by 1.2. So what it gets here is pH 7.4 plus minus 5/100 of a pH. You have to control it that well, the pH, to 5/100 of a pH unit, otherwise you get in trouble. For example, if you start hyperventilating, you decrease that pressure here in the lungs, you usually decrease it to 20 torrs, and with this the pH goes up. It goes up to 7.6, and you're getting in serious trouble. You get alkalosis, is that called. Yeah? And so, and you know what you do if somebody hyperventilates? Let them breathe them in a bag, but please a paper bag, not a plastic bag, okay? That the air can get in and out, all right? So that way you increase the pressure of CO2 in the lungs and you get them back to normal, all right? When you dive, all right, you would try to dive, and how long can I hold my breath underwater? That's what you did as a kid, okay? So that increases the CO2, it gets the pH up, it gets the pH down from 7.4. Once you reach 7.2, there's a switch in your brain that says, you have to breathe now, okay? I can't let that pH go below 7.2. You have to breathe now. That's why if you can try as hard as you want, you have to come up and get some air, okay? Some people can stretch it a little longer than others, but eventually the brain tells you, breathe, okay? pH is too low, all right? And so these are very serious conditions, and a change of 0.2 pH units in your blood pH is life-threatening already, right? So now let's talk a little bit more about polyprotic acids. And you have amino acids. Amino acids are the building stones of proteins and enzymes and all kinds of things. And they are also very, very pH dependent. Even the synthesis in your body is pH dependent. And they are polyprotic acids. So there's an amino acid that is called cysteine. And this has essentially 3 acidic centers. This has here, it is an acid COOH. So this one has a pKa of 2.2. Now, if I have pH 1, would that be on or off? That proton? On, okay? I go to pH 3, would it be on or off? Off, okay? So now we go up in pH, so we deprotonate this. Now we come to this one here, so this is now minus, and you see that NH3 is always plus here. It's protonated, okay? So we come to this one here, and we have now this SH, the thiol bond here. This H is acidic, but the pKa is 8. So I'm at pH 6. Is it on or off? On, exactly. I go to pH 9. Is it on or off? Off, exactly. So then you have a negative charge here. That would be that here. And you have 2 negative charges and 1 positive here so far. Now this NH here has a pKa of 9. So I'm at pH of 8. Is it on or off? On, okay? So the charge of this would be then, this would be positive, this would be negative. So it would be -1, the overall charge of this, okay? Now I go to pH of 10. I go to pH of 10. Is it on or off? It's off. So then you have an NH2 here, and this is neutral, has no charge. This is minus, and this is minus, okay? So this is an important issue, just for example, for protein folding and unfolding. If you have these negative charges on it, it unfolds because they repel each other. If it folds, you can't have that many negative charges. You can have a plus and a minus. Then it folds nicely. So this is all regulated by buffers and by pHs and so on. So this is something you will learn more than I know about this soon if you go into that field. So you see, this is a triprotic acid here. It has 1 proton here that's acidic, the second one, and the third one that's acidic, okay? So let's do an experiment. We're going to grind up some, what is it, rutabaga? No, what is it? Turnip. Karen's going to grind up some turnip, and we're going to make a turnip smoothie, okay? And turnips are extremely good for you. They have an enzyme. And what is that enzyme called? Peroxidase. You know, you hear about all these oxidizers that we need to get rid of in our body. And this gets rid of hydrogen peroxide in your body, which is generated during many reactions. So that kills H2O2. And with this, you live healthily. Eating turnip, raw turnip, you live healthily. So you get a smoothie of turnip every morning. And I want to show you this, that it destroys H2O2. So actually, turnip is not so bad. I never ate raw turnip. It's pretty good, actually. Didn't have lunch either, so. Okay. So I feel it already, how the H2O2 leaves my body. So that's peroxidase is the enzyme. And that enzyme we're going to put here. Looks beautiful. And so what did the peroxidase destroys? The peroxide to H2O and oxygen, okay? And so this is now water. That's sort of the pH that we have in our body. And this is acid, yeah? You're going to put some acid in there? So this is acid, this side, okay? This is acid. You see, we put a little indicator in there. Oh, look, it looks pretty, huh? Like Orange Julius. Okay, and this is, you see, is neutral. We learned about that indicator, it's this yellowish. So this is more like it's in the body, and this is what acid in an acidic form. You don't have that form, but I want to show what happens there. Okay, we're putting the peroxide in there. You see that? In the acidic form, it doesn't work that well, but it works beautifully in, I hope this doesn't happen in your body like this, that works beautifully here at the pH 7, and it's very much dependent on the pH. That peroxidase enzyme cannot react if it has the wrong pH, okay? So you see how it destroys, makes all this wonderful oxygen here and water, and so it makes it foam like you see here, and so this is peroxidase. Thank you, Karen, she is gone now, but so we see that pH is an important issue. So let me see, maybe I need that blender later a little bit, but for these Mexican concoctions. Or do they have margaritas somewhere else? Yeah, we have them here, isn't it? Okay, so now we have amino acids. This is lysine, that's another amino acid. So this is pKa, this is the carboxylic acid, that's the OH is minus here. So that's no. The hydrogen, the proton is gone, so it is negative now here. But what pH would that have that I have to make it negative? Would that be pH much larger than 2.2 or much smaller than 2.2? That's the pKa obviously here. Larger, much larger, okay? And then I have this NH3, they are always plus. So this goes off at pH 9, it's 50-50. So at this pH, if you have that, you have 50% on and 50% off, okay? And that's the same thing here, 50% on, pH 9, 50% NH2 and 50% NH3 plus. At this one, you need to go up to over 10 to remove that proton here. So if you remove that, then it's not plus anymore. You see that? Then it's NH2 and not plus. Okay? So at pH 7, this one stays on, and this one stays on, and this one is off. At lysine, for example, has a pKa of 2.2. This one here, this one is off, and this stays on, and this is obviously, well, this is an OH here. Okay? This doesn't come off immediately, so you need to go above pH 10, tyrosine. Okay? Now, this would be aspartic acid and histidine. So, and we can go through the spiel. So this one here is 3.9, the pKa, and this is 2. So this is off at pH 7. This is off minus, this is off minus, and this is plus because nothing happened here. So, and histidine, that is 1.8, the pKa here. The pKa is 6 here. So that obviously it's gone here, all right? There wasn't, and this here is NH3 plus, nothing happens here. Let me ask you a question. I have the amino acid cysteine. I showed you that. I didn't put any charges on here, okay? All the protons are on it. I didn't put any charges on there. So I want from you to know from you now, I have a pH of 5.5. What is the overall charge on this molecule? Is that 1 or 0 or minus 1? Think very carefully about this and give me your answer. I have no charges drawn. There are charges on there probably, but I have not drawn them. So now we have to remember what I've shown you in the previous pictures. So what is it? How about everybody in? Everybody? Let's have a look at it. Actually, the right answer has the lowest answers. Okay, it's B. All right, why? Quickly, I show you. Okay, this was plus always. Remember, I pointed this out several times. This was plus to begin with, okay? And the only one that goes off at pH, what was the pH of 5, is this one here. So this becomes negative, this is positive, with this at 0, the overall ion, okay? There it is. See that? That's always plus here. All right, I see you on Monday. Thank you.